Module 6. Lecture A. Thinking Recursively. By the end of this lecture, you will be able to explain the structure of a recursive function, including base and recursive cases, implement simple recursive algorithms such as factorial and Fibonacci in Python, and compare recursive and iterative implementations in terms of clarity and performance. Understanding recursive structure. Designing base cases. In any recursive solution, the most important part is defining a base case that safely stops the recursion. This base case acts as a stable endpoint that every chain of recursive calls must eventually reach. Without it, the recursion can continue indefinitely and exhaust system resources. A clear, well-designed base case guarantees that the process ends with a concrete result and forms the foundation of an effective recursive design. A base case is the simplest version of a problem that you can solve immediately without breaking it down further. For example, when sorting, a pile with 0 or 1 paper is already sorted, so that is a base case. In programming, base cases usually involve the smallest input, such as an empty list or a single element. The important point is that the base case must match the way you solve the larger problem so the overall solution works correctly. When designing base cases in recursion, they must be both correct and complete. Correctness means the base case result matches the intended behavior of the function, because any mistake here will affect all larger recursive cases. Completeness means every chain of recursive calls moves toward some base case, so the process eventually stops instead of looping forever. You should also think about edge cases, such as negative inputs or empty data structures, and decide whether they need their own base cases or can be converted to existing ones. Clear and well-considered stopping conditions create a reliable foundation for any recursive algorithm. Python code, designing base cases. This lesson shows how base cases allow recursive functions to stop safely. It uses the factorial function as an example. First, with a correct base case that ends the recursion and returns a final result. Then, it contrasts this with a version that has no base case, which keeps calling itself until it fails. By printing and comparing the results, you can clearly see the difference between safe recursion with a proper stopping condition and unsafe recursion without one. This line is a placeholder comment that shows where you would install a required Python library. It indicates that if your code depends on an external package that is not part of the standard library, you should install it using the Python Package Manager, pip. Including this reminder helps ensure that all necessary dependencies are installed so the script can run correctly. Factorial safe is a recursive function that computes the factorial of a number. It first checks whether the input is 0 or 1, which is the base case, and in that situation it returns 1, since the factorial of both 0 and 1 is 1. If the number is larger than 1, the function multiplies the current number by the result of calling itself with the number reduced by 1. This process repeats until the input eventually reaches the base case, which guarantees that the recursion stops correctly. In this example, we define a factorial function that is intentionally unsafe because it does not include a proper base case. The function keeps calling itself with the current number multiplied by the factorial of 1 less than that number. Since there is no stopping condition, this recursive process never ends. As a result, the program eventually hits the maximum recursion depth and produces an error, illustrating why every recursive function must have a clear base case. We use a safe factorial function to compute the factorial of 5. This function includes a base case, so the recursive calls eventually stop. The final value, which is the factorial of 5, is then stored in a result variable. This approach ensures the recursion terminates correctly and produces the intended answer. This code calls a safe factorial function with the input 5 and prints the result. The function uses recursion and stops correctly when it reaches its base case, so it does not run into errors. The output message states that the safe factorial of 5 equals the computed value, making it clear that the recursive process finished successfully. When we run an unsafe factorial function with an input of 5, it fails because it has no proper base case, so it keeps calling itself forever. This endless recursion eventually exceeds the system's recursion depth limit and triggers a recursion depth error. To manage this, we wrap the call in a try-except block so that when the error occurs, the except part catches it and reports that the unsafe factorial failed due to a recursion error. This example highlights why every recursive function must include a correct base case to avoid infinite recursion. This script uses the factorial calculation to show why base cases are essential in recursive functions. It first defines a safe factorial function that correctly treats 0 and 1 as stopping points, so the recursion ends and the factorial of 5 is computed and printed as 120. It then defines an unsafe factorial function with no base case, which causes infinite recursion when called with the same input. This eventually triggers a recursion depth error that the script catches and reports as a failure caused by the missing base case. The comparison highlights that without proper base cases, recursive functions can run forever and crash instead of producing a result. Building recursive steps. After defining the base case in a recursive function, you must design the recursive step, where the function calls itself on a simpler version of the problem. The idea is that if the problem is not simple enough to solve directly, you transform it into an easier one and pass that to another call of the same function. Each recursive call must move the problem closer to the base case to avoid infinite recursion. For example, when working with a list, you might process the first item, then call the function again on the remaining items, repeatedly breaking the task into smaller parts until it reaches the base case. In a good recursive step, each function call solves a smaller, genuinely simpler subproblem, then combines that result with the work at the current level. You can think of every call as adding its own contribution to the final answer. For instance, when summing numbers recursively, you add the first number to the sum of the remaining numbers. In a maze problem, you choose a direction and let the recursive call search for a path, then use its success or failure when you return. In this way, the full solution is built layer by layer as each recursive call finishes and passes its result back. In recursion, you can think of each function call as passing a smaller version of the problem down the call stack and waiting for an answer. This continues until a base case provides a simple, definite result. That result then travels back up, with each returning call modifying or extending it, like adding steps to a path. When designing the recursive step, you must be clear about what each call sends down, what it expects to get back, and how it transforms that returned value into part of the final solution. Python code, building recursive steps. We will illustrate how to build recursive steps using a simple example that sums the elements of a list. Each recursive call will process one item from the list and then delegate the remaining work to the next call, showing how the problem becomes smaller at each step. We will also print messages during each call so you can hear how the problem shrinks and how the partial results are combined into the final sum. No special external libraries are required beyond the standard ones. We define a recursive sum function that adds all the elements in a list step by step. It begins by checking whether the list is empty, which serves as the base case in the recursion. If the list is empty, it reports that the base case has been reached and returns 0. This 0 value forms the starting point for building the total sum as the recursive calls finish and return their results. In this recursive function, the code first takes the initial element of the list as the current item to process. It then separates the remaining elements into a smaller list that will be used in the next recursive step. A message is printed to indicate which element is being handled and what part of the list will be passed on. Finally, the function calls itself with this reduced list, passing the task of summing the rest of the elements to the next recursive call. In this step of the recursive process, the code adds the current value to the result of the smaller subproblem, gradually building the total as the recursion returns. It then prints a message that shows this combined result and clarifies that it comes from adding the current value to the smaller sum. Finally, it returns this combined value so that each level of the recursive function can continue accumulating the overall total. We begin with a simple list of distances in miles: 5, 10, and 3. This list serves as an example to show how a recursive function processes each value. The function handles each distance one at a time and then combines the results. By using this small set of numbers, it is easy to see how the recursive process builds up to the final total sum. We start by calling the recursive sum function on the list of distances, which begins the process of adding the elements one by one. The function works through the list recursively until it has combined all the values. When the recursion finishes, we print the final total distance. This final value represents the complete sum of all distances in the list and shows the result of the recursive summation. This script shows how recursion can be used to sum the elements of a list. It begins with a base case that checks if the list is empty and returns 0 in that situation. For a non-empty list, it takes the first element, then calls itself again with the remaining elements. Each recursive call prints the current element and the rest of the list, and as the calls return, it adds each element to the partial sum and prints the intermediate results. In the example, it adds the distances 5, 10, and 3 to produce a final total of 18. Tracing the call stack. To understand recursion, imagine each function call being placed on a stack. When a recursive function calls itself, the current call is set aside but not forgotten, and the new call is placed on top. When a call finishes, it is removed from the top, revealing the previous one underneath. This last-in, first-out behavior lets recursion break a problem into smaller pieces and then rebuild the final answer as each call returns. Grasping this stack process is essential to mastering recursion. Tracing the call stack means following each recursive call as it is added and removed, so you can see how the program moves forward step by step. Each call keeps track of where it came from and what work is still pending. As you move from the first call down to the base case and then back up, you see tasks finish in reverse order. This shows that recursion is simply a structured way to postpone parts of a task until smaller subproblems are solved. Not a mysterious process. Tracing the call stack is essential for debugging recursive algorithms because it shows which function calls are currently active and how data moves between them. By mentally following the call stack, you can check whether your recursion is correct and efficient, estimate recursion depth and memory use, and spot problems such as missing base cases or infinite loops. In short, understanding the call stack helps you verify that your recursive logic behaves as intended. Python code, tracing the call stack. Use a simple countdown example to demonstrate how recursive calls build up on the call stack. Each time the countdown function calls itself with a smaller number, the current call is paused and waits on the stack while deeper calls continue. By printing clear messages when entering a recursive call and when returning from it, you can trace exactly how the calls go down to the base case and then unwind back up. Standard libraries are enough for this demonstration, so no extra installation is required. The countdown with trace function is a recursive example that takes a number and a depth value and prints messages showing how the call stack changes. When it starts, it announces that it is entering a call at the current depth with the current number. It then checks whether the number is 0, which is the base case where recursion stops. And if so, it prints that the base case has been reached. If the number is not 0, it calls itself again, with the number decreased by 1 and the depth increased by 1. After each deeper call finishes, it prints a message that it is returning at the current depth, letting us see how each call waits on the stack until all deeper calls complete. The countdown function starts with a value of 3 and a depth of 0, then repeatedly calls itself with the value decreased by 1 and the depth increased by 1. Each call announces its current depth and value, showing the progress of the recursion. When the value reaches 0, the base case is hit and a message indicates that the recursion has stopped going deeper. As the function returns from each call, it prints messages showing it is moving back up to the previous depth. This sequence of messages provides a clear trace of how the call stack grows and then unwinds during recursion. This Python script uses a simple countdown to show how a recursive function works and how the call stack behaves. As the function repeatedly calls itself with smaller values, it prints messages that indicate the current depth and the value being processed. When the base case is reached, where the value becomes 0, the recursion stops. The script then prints messages as each call returns, illustrating how the stack unwinds step by step. Overall, it provides a clear, high-level view of how Python manages recursive calls and returns using the call stack. Classic recursive algorithms. Recursive factorial basics. Factorial counts how many ways you can arrange a set of items, and recursion is a natural way to compute it. The recursive idea is to choose the first item, then recursively arrange the remaining items so the function calls itself with a smaller input each time. This continues until it reaches a base case, such as arranging 0 or 1 item, where the answer is immediate. The base case is essential because it stops the recursion and provides a simple, known result to build on. To implement a recursive factorial in Python, you first define a base case that stops the function from calling itself further. For factorial, the base case is when the input is 0 or 1, because there is only one way to arrange these. You then define the recursive case, where you assume you can compute the factorial of the input minus 1 and use that result to get the factorial of the current number. The function checks whether the input matches the base case, and if not, it calls itself with a smaller input. This pattern of checking a base case and then making smaller self-calls is a standard structure for recursive functions, clearly illustrated by the factorial example. To understand recursive factorial, imagine computing it for the number 4, where each function call asks for the factorial of the next smaller number until it reaches 1. The value at 1 is the base case, which returns a simple result. Then each previous call resumes and combines its result with the one returned from the next call, building the final answer step by step. This is similar to breaking a project into smaller tasks, completing the simplest ones directly, and then combining them to finish the whole project. Thinking about recursion this way helps clarify how recursive algorithms in Python break complex problems into simpler, manageable pieces. Python code, recursive factorial basics. This lesson introduces the basics of computing factorials using recursion in Python. It explains how to define a clear function with a base case where the recursion stops and a recursive case where the function calls itself with a smaller positive integer. Simple examples with small positive numbers show how each call builds on the previous one. Finally, it suggests printing the results for several inputs so you can see the recursive pattern unfold step by step. This script uses only the standard Python libraries, so you do not need to install any extra packages before running it. As long as you have a basic Python environment set up, you can execute the code right away. This makes the script simple to use and accessible to anyone with a standard Python installation. We define a factorial function that takes a single input value. Inside the function, we first check whether this value is 0 or 1. In that case, we know the factorial is 1, so we immediately return 1 as the result. This simple check is called the base case, and it is essential because it stops the recursive process from continuing forever and guarantees that the function eventually finishes and returns a value. In this step of the factorial function, we handle the recursive case by multiplying the current number by the factorial of that number minus 1. The function keeps calling itself with smaller and smaller values until it reaches the base case, where the input is 0 or 1. At that point, it returns 1. By chaining these multiplications together, the function builds the factorial as the product of all the integers from the original number down to 1. We will use a small list of test values, specifically 0, 1, 2, 4, and 6, to explore how the factorial function behaves. These simple integers keep the results easy to read and understand. By focusing on these values, we can clearly see the recursive pattern of the factorial function without adding unnecessary complexity. We go through each test value in the list, and for each one, use the recursive factorial function to compute its factorial. After calculating the result, we print a clear message that shows both the original value and its factorial. This process lets us see how the recursive function behaves for different inputs and confirms that it is working correctly. This Python script shows how to compute factorials using recursion. It defines a function with a base case for inputs 0 and 1, and a recursive case for inputs greater than 1. In the recursive case, it multiplies the current number by the factorial of the number -1, breaking the problem into smaller steps until it reaches the base case. The script then tests this function with the values 0, 1, 2, 4, and 6, and prints the factorial result for each input to illustrate how the recursive process works. Recursive Fibonacci Basics. The Fibonacci sequence is a clear example of how recursion mirrors a problem structure. Each term is defined using earlier terms, just as a recursive function calls itself with smaller subproblems. We first set base cases, such as the initial values of the sequence, to stop the recursion from continuing forever. All other terms are then defined in terms of previous ones, so the process alternates between returning known values and breaking the problem down until it reaches these simple cases. This shows how recursion works by repeatedly reducing a complex task into smaller, manageable parts. When we trace a recursive Fibonacci function, we see a branching pattern in the call stack. For any input that is not a base case, the function calls itself twice with smaller indices. Each of these calls either returns immediately if it reaches a base case or continues branching in the same way. This creates a tree-like structure where internal nodes split into two calls and the leaves are the base cases. Overall, the function repeatedly breaks the problem into simpler parts and then combines the results to produce the final Fibonacci value. The recursive version of the Fibonacci function closely matches its mathematical definition, but it becomes inefficient because each non-base call triggers two more calls and repeats many calculations. This makes it slow as the input size grows. So while it is useful for teaching and understanding the concept, it is not ideal for performance. An iterative approach is usually faster because it builds the sequence step by step and reuses previous results. In practical applications, this trade-off leans to techniques like memoization and dynamic programming, which keep the clarity of recursion while greatly improving efficiency. Python code, Recursive Fibonacci Basics. Explain the recursive Fibonacci function by clearly stating its base cases, where the smallest inputs return fixed values, and its recursive case, where each call computes a value by calling itself on smaller inputs. Describe how these recursive calls branch out like a tree, with each call spawning 2 more calls until they reach the base cases. Then, show how the results from the leaves of this tree combine as the calls return, building up to the final Fibonacci value. Finally, compare the results for small input values to make the pattern of recursion and its rapid growth easier to understand. This script only uses standard Python libraries, so you do not need to run any pip install commands. Because it relies entirely on built-in functionality, there's no need to add external packages. This makes the script easy to run without extra setup. Users can simply use their existing Python installation and start the code right away. We define a recursive function to compute Fibonacci numbers, where the input is the position in the sequence. The function checks if the position is 0 or 1, and in those base cases, it simply returns that same value. This works because the Fibonacci sequence begins with 0 at position 0 and 1 at position 1. For any other position, the function would use recursion, but for these starting values, it returns immediately without further calls. In this part of the code, we handle the recursive case for computing Fibonacci numbers by having the function call itself twice with smaller inputs. One call uses the input -1 and the other uses the input -2. These two results represent the 2 previous Fibonacci numbers. The function then adds these 2 values to obtain the Fibonacci number for the current input, directly matching the mathematical rule that each Fibonacci number is the sum of the 2 preceding numbers. We begin by setting the index value to 5. Choosing a small index keeps the number of recursive calls low. This helps avoid performance problems and makes the recursive process easier to manage and understand. We use a recursive function to compute the Fibonacci number at a chosen index, such as 5. The function repeatedly calls itself, breaking the original problem into smaller subproblems until it reaches simple base cases. It then combines the results of these smaller problems to produce the Fibonacci number at the desired position. This process illustrates how recursion branches into multiple calls that eventually come together to form the final answer. The code prints a message to the console that identifies which Fibonacci number was calculated and what its value is. It reports the position in the sequence stored in the index variable and the corresponding Fibonacci number returned by the recursive function. This combined message clearly shows both the input position and the resulting Fibonacci value, making it easy to check that the function is working correctly. To better understand the Fibonacci sequence, we look at the numbers from 0 through 5 and compute the Fibonacci value for each one using a recursive Fibonacci function. For every number in this range, we pair the index with its corresponding Fibonacci value. Saying these pairs out loud shows how the sequence begins and how the values grow step by step for small inputs. This script shows how to compute Fibonacci numbers using recursion. It defines a function that directly returns results for 0 and 1. And for any larger number, It calls itself to add the two previous Fibonacci values. The script then calculates the Fibonacci number at position 5, which is 5, and prints it. It also loops through the first 6 positions, printing each index and its corresponding Fibonacci value. This example illustrates how recursive calls branch out and then combine results, and how the number of calls grows rapidly as the index increases. Recursive list patterns. After learning recursion with numbers, such as factorials or Fibonacci, the next step is to apply the same idea to lists. A list works well for recursion because it is either empty or made of a first element followed by the rest, which naturally gives you a base case and a smaller subproblem. For example, to sum a list, you treat it as the first element plus the sum of the remaining elements, with the empty list having a sum of 0. This pattern of handling the first element and then recursing on the rest is central to understanding recursive algorithms on lists. Recursion on lists can be used for tasks like counting, filtering, and transforming data by repeatedly handling one element at a time. For counting, you check whether the first item meets a condition, treat that as 1 or 0, and add it to the count from the rest of the list. For filtering, you decide whether to keep or discard the first element, then combine that choice with the filtered remainder. For transforming, such as converting temperatures, you change the first element and attach it to the transformed rest of the list. In all these cases, the base situation is an empty list, which returns 0 or an empty result, and the recursion works by reducing the list until it reaches that base. Recursive patterns with lists are especially helpful for understanding real-world data, such as stock prices, sensor readings, or website clicks. Even though these tasks are often implemented with loops for efficiency, thinking about them recursively clarifies the structure of the problem. You focus on processing one element at a time and let the recursive call handle the rest of the list. This mindset helps you recognize base cases and reduction steps, much like when working with factorials or Fibonacci sequences. Python code, recursive list patterns. This material focuses on using simple numeric examples to show how recursion works with Python lists. It demonstrates recursive patterns for operations such as summing the elements, counting items, and transforming each value in a list. The examples highlight how each function handles the base case, like an empty list, and then the recursive case, where the function calls itself on a smaller part of the list. The results are printed to clearly contrast what happens in the base case versus the recursive step. This line is a placeholder comment that reminds you to install a required library if your code needs it. It marks the spot where you would add a command to install a Python package using the package manager. This is important when your program depends on external libraries that are not included in the standard library. Including this step helps ensure all necessary dependencies are installed so the code can run correctly. A recursive sum function takes a list of values and adds them together using recursion. It first checks whether the list is empty. If it is, it returns 0 as the base case, which stops the recursion when all elements have been processed. If the list is not empty, the function adds the first element to the result of calling itself on the rest of the list. By repeatedly breaking the list into the first element and the remaining elements, it eventually reaches the empty list and produces the total sum of all values. we define a function that counts how many elements in a list are greater than a given threshold. It first checks if the list is empty. If so, it returns 0 because there is nothing to count. Otherwise, it looks at the first element and assigns a value of 1 if this element exceeds the threshold, or 0 if it does not. The function then adds this value to the result of calling itself on the rest of the list, building up the total count of elements above the threshold as it goes. We define a recursive function to convert a list of inch values to centimeters. It first checks whether the list is empty, and if so, returns an empty list as the base case, so the recursion stops. Otherwise, it converts the first value by multiplying it by 2.54, then creates a new list starting with this converted value. The function then calls itself on the remaining elements, gradually building a complete list of centimeter values from the original list of inches. We begin with a simple example list of daily rainfall depths measured in inches. This list contains 4 values, 0.5, 1.2, 0, and 0.8. These values will serve as our sample data. We will use them in later steps to show how recursive techniques can be applied to process lists. We calculate the total rainfall using a recursive sum function that takes a list of rainfall measurements in inches and returns their total. The function works by breaking the list into smaller parts and adding the first value to the sum of the remaining values. When it reaches an empty list, it returns 0 as the base case. By calling this recursive function on our rainfall data, we obtain the total rainfall in inches. We use a recursive function to count how many days had more than half an inch of rain. The function takes a list of daily rainfall amounts and a threshold of 0.5 inches. For each day, it checks whether the rainfall exceeds the threshold, and if so, adds 1 to the count. It then moves on to the next day in the list until all days have been checked. The final result is stored as the total number of days that meet this rainfall condition. We use a recursive function to convert a list of rainfall measurements from inches to centimeters. The function takes the list of inch values as input and processes one element at a time. For each value, it multiplies the number of inches by 2.54, which is the standard conversion factor to centimeters. It then builds a new list by combining this converted value with the result of recursively converting the rest of the list, so the entire list is transformed from inches to centimeters. We begin by displaying the original list of rainfall measurements in inches to confirm the input data. We then show the total rainfall in inches computed using a recursive sum function to understand the overall amount of rain. Next, we report how many days had more than half an inch of rain, using a recursive counting function to highlight how often significant rainfall occurred. Finally, we present the same rainfall measurements converted to centimeters with a recursive conversion function, giving a clear metric version of the data. This script uses a simple list of daily rainfall measurements in inches to demonstrate recursion on lists. It defines 3 recursive functions, one that adds all the rainfall values, one that counts how many days exceed a chosen rainfall threshold, and one that converts each value from inches to centimeters. When run, The program prints the original list, the total rainfall in inches, the number of days with more than half an inch of rain, and the converted list in centimeters. Together, these operations clearly show how base cases and recursive calls work in a practical Python example. Recursion versus iteration. Understanding tail recursion. To understand recursion versus iteration, it helps to look at tail recursion. In tail recursion, the recursive call is the final action before the function returns, so no extra work is needed afterward. The function simply passes along an updated running result to the next call, much like a loop that repeatedly updates variables and checks a condition. Because it never needs to revisit earlier steps, tail recursion behaves very similarly to iteration in both flow and clarity. Tail recursion is interesting for performance because many languages can optimize it to use constant stack space, much like a loop. With this tail call optimization, the system reuses the same stack frame for each call, which avoids stack overflow and keeps memory usage similar to iteration. When this optimization is available, the choice between tail recursion and loops usually depends on clarity and coding style rather than speed. For instance, processing a long list with a tail recursive function that maintains a running total can be just as efficient as using a loop, as long as the language supports tail call optimization. Thinking in terms of tail recursion helps you see how recursive and iterative solutions are related. When you convert a regular recursive function into a tail recursive one, you make the loop-like structure explicit by using accumulators and ensuring each step finishes before the next begins. This reveals which parts truly depend on the call stack and which could be written as loops. In practice, such as refining estimates or traversing trees, recognizing when to reshape recursion into tail recursion or an iterative form lets you compare options more systematically and balance the clarity of recursion with the predictable performance of loops. Python code: Understanding tail recursion. This lesson compares a simple tail recursive approach and an iterative approach for summing numbers. It explains how tail recursion uses an accumulator to carry a running total through each recursive call. By following how the accumulator is updated, you can see that the recursive process mirrors what a loop does step by step. Finally, you compare the outputs to confirm that both recursion and iteration produce the same sum efficiently. This line is simply a reminder that you might sometimes need to install extra libraries with a package manager, but for this particular code, the standard Python library is enough. It tells you that no additional installations are required right now. The main purpose is to prompt you to think about dependencies if you later adapt or expand the code. We define a recursive function to compute the sum of the numbers from 1 up to a given value n. The function checks whether n is 0 as its base case. If so, it returns 0 and stops. If n is not 0, it returns n plus the result of calling itself with n decreased by 1. This process repeats until n reaches 0, and then the partial sums are combined as the recursion unwinds to produce the final total. In a tail recursive function for summing numbers, we use an extra parameter called an accumulator to store the running total. The function checks whether the input number is 0, and if so, returns the accumulator as the final sum, which serves as the base case that stops the recursion. If the number is not 0, the function calls itself with the number reduced by 1 and the accumulator increased by the current number. Because this recursive call is in tail position, it carries the updated total forward without leaving any work to do afterward, which makes memory use more efficient. To sum numbers iteratively, we keep a running total that starts at 0 and use a loop that continues while the input number is greater than 0. During each pass through the loop, we add the current number to the total, then decrease the number by 1. This process repeats, accumulating the sum of all positive integers down to 1. When the number reaches 0, the loop ends and the function returns the final total, which is the sum of the original number down to 1. We choose a small number, 5, so the results are easy to read and understand. Using this simple value lets us clearly show how both the recursive and the iterative versions of the sum function work. It keeps the focus on the process rather than on handling large or complicated numbers. This makes the demonstration more accessible without changing the underlying idea. We compare 3 ways to compute the sum of numbers from a given value down to 1. First, a standard recursive function calls itself and adds each number until it reaches 1. Second, a tail recursive version passes along an accumulator that keeps the running total, so no extra work is needed after each recursive call. Third, an iterative version uses a loop and a total variable to add the numbers step by step. All 3 methods produce the same result, allowing us to directly compare how they work. We compare 3 ways to compute the sum from 1 up to a chosen number. First, we print the result from a standard recursive sum function. Then, we print the result from a tail recursive version that uses a different recursive style. Finally, we print the result from an iterative version that uses a simple loop. Seeing that all 3 outputs match shows that these different approaches are equivalent for calculating the same sum. This script compares 3 ways to add all the numbers from 1 up to a given value: a standard recursive method, a tail recursive method, and an iterative loop. The non-tail recursive version waits for each deeper call to finish before adding the current number. The tail recursive version instead carries a running total, so each call can complete immediately. The iterative version uses a simple loop to accumulate the sum. When run with the number 5, all 3 approaches produce the same result, showing they are equivalent in outcome, though tail recursion and iteration are often more efficient in how they use memory and manage state. Python recursion limits. In Python, recursion is limited by the runtime environment because each recursive call creates a new stack frame, and there is a maximum recursion depth to prevent crashes. If your recursive function goes too deep, it will trigger a runtime error. Iteration, on the other hand, reuses a single stack frame for loop execution. This means iterative solutions use fixed stack space and are much less likely to run into these depth limits. When choosing between recursive and iterative designs, it is important to consider recursion limits, especially for large problems. Recursion can be elegant and works well for small tasks, but as input sizes grow, it may exceed Python's maximum recursion depth and cause the program to fail. This is a risk in situations like processing very long dependency chains. Iterative approaches that use loops with explicit stacks or queues avoid these depth issues and are generally more reliable for large-scale inputs. Python's recursion limits can hurt performance and robustness, especially for deep or unbounded calls. Recursion often runs slower and uses more memory than loops, and Python does not optimize tail recursion. In areas like data analytics or web crawling, this can make programs fragile, since large inputs may trigger confusing runtime errors. Understanding these constraints helps you reserve recursion for naturally small or bounded problems and rely on loops when you need predictable speed and resilience. Python code. Python recursion limits. This lesson uses a simple factorial example to demonstrate Python's recursion depth limits. It compares a recursive version of factorial with an iterative version when the input size becomes large. By observing when the recursive approach hits the maximum recursion depth or slows down, and how the iterative approach continues to work, you can see how recursion depth affects both reliability and performance. This helps explain why, for large problems, an iterative solution is often the safer and more efficient choice in Python. The script points out that you do not need any pip install commands because it uses only built-in Python features. This means the code does not depend on external libraries and will run in any standard Python setup without extra configuration. As a result, it is more portable and easier to use, which is especially helpful when demonstrating ideas like recursion limits and factorial calculations. We begin by importing the system module so our program can interact with the Python runtime environment. This module lets us access and adjust system-level settings, such as the recursion limit. Controlling these settings is important for safely handling recursive functions that might go deeper than the default limit. By using the system module, we can manage recursion depth issues more effectively and keep our code running reliably. The code increases the allowed number of digits when converting an integer to a string to 100,000 using a system-level setting. This change raises the default limit so that very large integers can be safely converted without errors. It is especially useful for operations like computing large factorials, where the resulting numbers can have far more digits than the original default limit permits. By adjusting this limit, the code helps prevent a value error during these conversions. This description explains a recursive way to compute the factorial of a number. The function first checks whether the input is 0, and if so, returns 1, since the factorial of 0 is 1. Otherwise, it calls itself with the number reduced by 1 and multiplies that result by the current number. This process repeats until the input reaches 0. And the chain of multiplications produces the factorial of the original number. However, for very large inputs, this recursive method can fail because it creates a call stack that is too deep. To compute the factorial of a number without recursion, we can use an iterative method. We begin by setting a running total to 1, which will store the final factorial value. Then we loop from 1 up to the input number, and during each pass, we multiply the running total by the current loop value. By the time the loop finishes, we have multiplied all integers from 1 to the input number, and the running total now holds the factorial, which we then return. We choose a very large input value such as 2000 to test how far Python's recursion can go before hitting its depth limit. Using this large number with a recursive factorial function creates a very deep chain of function calls, which can lead to a recursion depth error. This experiment helps us observe how the recursive approach behaves under stress and compare its performance and reliability with an iterative method for computing factorials of large numbers. This code displays the current recursion limit by calling a system function that reports how deep the call stack is allowed to go. Knowing this limit helps you understand how many nested function calls can occur before the program stops with a recursion error. This is especially important when working with recursive functions that might reach or exceed that maximum depth. We use a recursive factorial function on a very large number to test whether it exceeds the maximum recursion depth. If the computation finishes, we report that the factorial was successfully calculated for that number. If a recursion depth error occurs instead, we catch it and report that the recursion limit was reached. This experiment shows the practical limits of using recursion for large inputs. To compute the factorial of a large number, we use an iterative method instead of recursion. In this approach, the function repeatedly multiplies numbers in a loop and stores the final result in a variable. This avoids recursion depth limits that can cause errors with very large inputs. As a result, the iterative factorial method is more reliable and efficient for handling large values. This statement confirms that the iterative method for computing the factorial has successfully finished for the large input of 2000. It shows that the iterative approach works reliably even for very large numbers. It also emphasizes that this method avoids the recursion depth problems that a recursive approach might encounter with such large inputs. When computing a factorial, the result can become extremely large, so instead of trying to display the whole number, the code converts the result to a string. This makes it easy to count how many characters or digits are in the number. By using the length of this string, we can quickly find out how many digits the factorial has. This approach lets us describe the size of the result efficiently without handling or printing the entire huge value. This script demonstrates Python's recursion depth limit by comparing two ways to compute a factorial. It uses a recursive version that can fail with a recursion error for large inputs, such as 2000, because it exceeds the maximum call depth. It also uses an iterative version that avoids recursion and reliably computes the same large factorial. The script prints the current recursion limit, then shows that the iterative method succeeds and reports how many digits are in the result, highlighting the greater reliability and performance of the iterative approach. Prefer iteration cases. In many situations, an iterative approach is not just an alternative to recursion, but the better option, especially for simple, linear passes over data. When you scan a file, process sensor readings, or update database records, a straightforward loop is usually clearer and more efficient because these tasks do not break into smaller subproblems. Iterative loops make the control flow easy to see, from where it starts to where it ends, which lowers the mental effort needed to understand the code. This clarity is particularly important in collaborative or long-term projects, where others must be able to read and maintain the code effectively. In many real-world programs, iteration is preferred over recursion because it uses fewer resources and is more efficient. Recursive calls create new stack frames each time, which can slow execution and even cause stack overflow when the recursion is very deep. Iterative loops reuse the same stack frame and track progress with a fixed set of variables, making them faster and more memory efficient, especially in systems that do not optimize recursion. For tasks that involve an extremely large number of steps, such as simulating vehicle movement or processing high-resolution images, iteration is usually the safer and more scalable choice. In many real-world systems, iteration is preferred over recursion because it offers finer control over how a process runs and how errors are handled. With iteration, you can pause, resume, or roll back steps and manage exceptions more directly. This is useful in situations like servers handling network requests or data pipelines that need logging and recovery steps. Although recursion can support these features, it often makes the code more complex, while iteration keeps the logic clearer and easier to manage. Python code. Prefer iteration cases. We want to show that iteration is usually clearer and safer than recursion when performing long sequences of simple repeated steps. For example, when accumulating distance over many miles, an iterative loop makes it easy to keep adding to the total in a straightforward way. A recursive version doing the same accumulation can quickly run into limits, such as maximum recursion depth, making it less reliable for large inputs. In contrast, iteration remains efficient, avoids these limits, and is generally the better choice for long-running, repetitive calculations, even if you need to install supporting libraries beforehand. The code first imports the system module, which lets Python access internal interpreter settings. It then raises the recursion limit to 10,000 using the function that controls maximum recursion depth. This change allows recursive functions to call themselves many more times than the default setting permits. While this can be useful for algorithms that need deep recursion, it also increases the risk of a stack overflow if the recursion is not carefully controlled. The recursive miles function calculates total distance traveled using recursion. It takes the total miles to travel, the current mile, and a fixed step size. If the current mile is greater than or equal to the total miles, it returns the current mile and stops. Otherwise, it calls itself again, with the current mile increased by the step size. This repeated self-calling process continues until the stopping condition is met, accumulating the distance step by step. This function, called iterative miles, calculates total distance using repeated addition. It takes a target distance and a step size, then starts from 0 miles traveled. Inside a while loop, it keeps adding the step size to the current distance as long as the current distance is still less than the target. When the loop finishes, the function returns the final value of the current distance, which represents the total miles accumulated. We choose a moderate total distance of 1,000 miles so that a recursive solution can run safely without exceeding system limits. We then set a small step size of a quarter mile. This step size is used to add up the distance piece by piece in both the recursive and the iterative versions of the algorithm. Using the same step size in both methods lets us fairly compare their performance and results. We compare recursive and iterative approaches for calculating the miles in a small trip. In the recursive version, a function repeatedly calls itself, adding a quarter mile each time until the total trip distance is reached. In the iterative version, a loop adds the same quarter mile step over and over until it reaches the same total. Both methods produce the same result, showing that recursion and iteration can solve this distance calculation problem equally well. We first print the result of the recursive method for a small trip to see how many miles it accumulates. Then we print the result of the iterative method for the same trip. Comparing these outputs shows that both methods produce the same number of miles. This confirms that the recursive and iterative approaches are both correct and work well for smaller tasks. Imagine a very long trip of 100,000 miles that must be covered through many repeated steps. If we tried to model this process using recursion, the program would create an extremely deep chain of function calls. This deep call stack would eventually cause a stack overflow error. This example shows that recursion is not well suited for very long linear processes. In such cases, using iteration is a more practical and reliable approach. To calculate the total miles for a large trip, we use an iterative method that repeatedly adds a fixed step size to a running mile count until the target distance is reached. This approach is efficient because it performs the computation through simple repeated addition in a loop. It also avoids the risks of recursion, such as stack overflow, making it safer for handling very large or repetitive tasks. Overall, the iterative method is a clear and reliable way to manage extensive mileage calculations. This code prints the result of the large trip calculation using an iterative method. It illustrates how iteration can efficiently handle many repeated steps. Unlike recursion, iteration avoids problems such as stack overflow. Overall, it highlights why iteration is often better for long, linear processes. The final line of the code summarizes why iteration is preferred for long, linear processes. It explains that iteration is clear, efficient, and safe when handling many repeated steps. This supports the idea that iterative methods are usually more robust and manageable than recursion, especially for large-scale tasks. This script compares recursion and iteration for a task that repeats many small steps to accumulate miles traveled. For a relatively small trip, both recursive and iterative approaches work and give the same result, showing that recursion can handle moderate workloads. But when the total distance becomes very large, the recursive version would cause a stack overflow because it creates too many nested calls, while the iterative version still runs safely and efficiently. The main conclusion is that for long, linear processes with many repeated steps, iteration is usually the better choice because it stays clear, efficient, and avoids the risks associated with deep recursion. In this lecture, you learn to explain the structure of a recursive function, including base and recursive cases, implement simple recursive algorithms such as factorial and Fibonacci in Python, and compare recursive and iterative implementations in terms of clarity and performance. In the next lecture, Lecture B, we will go over backtracking patterns.
Thank you for your attention. See you all in the next lecture.